In this video, we're going to work example problems involving testing series for convergence or divergence using the alternating series test. Now, just note that this name is a little deceiving. It almost implies that this test can be used for any alternating series, and that's not the case. It's only certain types of alternating series where so any alternating series can be written this way with a positive portion and then the alternating sign portion. But then the positive portion needs to satisfy this criteria. You could potentially have an alternating series that doesn't decrease like this. I mean, in general, it's obviously going to have to be decreasing in some sense to be convergent, right? But this isn't technically all encompassing for all possible alternating series. Okay, so here's an alternating series. Let's get the formula for the a sub n. So we've got, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. So the numerator is an arithmetic sequence with common difference 2. So that is first term 2 plus, and then the common difference times n minus 1, assuming we're starting at n is equal to 1. Okay, this looks, in the denominator is an arithmetic sequence with common difference 1. Okay, and then we're starting with a negative value. So if we're starting at 1, then we want to put n. Because when n is equal to 1, we have this negative. So we'll end up with with n is equal to 1, we end up with negative 2/5. So we've got 2 plus 2n minus 2, 5 plus 5n minus 1. So the a sub n here is plus, okay. Okay. So that's this is the sum from n is equal to 1 to infinity That's what this is. All right, so qualify for the alternating series test, any alternating series you can write like this, where the b sub n is the positive portion. Like the b sub n represents you can think about that like the b sub n is equal to the absolute value of a sub n. Okay, so we need to make sure that b sub n is decreasing from 1 to infinity, or at least from some n to infinity. So is 2n over 5n plus 4, right? So yeah, b sub n is that decreasing? Well, just looking at this, we might be able to just go ahead and use the test for divergence, because this looks like it might diverge. So, okay, the test for divergence is we just do this. For any series, the test for divergence, we take the limit as n goes to infinity of the a sub n. Right? Well, okay, what is this limit as n goes to infinity? If you divide the numerator and denominator by n, then this goes to 2/5. And so this limit is like minus 1 to the infinity times 2/5. And so what is minus 1 to the infinity? That's oscillating between minus 1 and 1. So this is an oscillating divergence. So since the test for divergence, since the a sub n if the a sub n of any sequence of the sequence of any series diverges, then the corresponding series always diverges. So we didn't even need to use the alternating series test here. So we've got the a sub n. Well, okay, we see what the a sub n is, but what's the b sub n? That's Okay. Now, is this decreasing? Yeah, it is. The 1 is always 1, and this is always getting bigger as n gets bigger. Okay, so what? So all right, so this satisfies the criteria for the alternating series test. So what is the alternating series test? Well, if it satisfies this criteria, then you just take the limit of the b sub n, and if that is equal to 0, then the series alternating series is convergent. Right? This is similar to the test for divergence, but in this case, we can actually, if the sequence of this series, the b sub n portion, converges to 0, then we can actually make a conclusion about the corresponding series. So we take the limit as n goes to infinity, and this is equal to 0. So this series converges. Okay, we can see that the b sub n is okay, and so, well, okay, this is another one of those that it looks like we can use the test for divergence, because I can see this limit's going to be 3/2. But I mean, is this decreasing? Let's start there. Is this decreasing? Let's try and use the alternating series test. So we can figure that out by, can we substitute for n a continuous variable x, and there's no issue. Yeah, there's no issue. I mean, you could divide by 0, well, not going from x equals 1 to infinity, so there's no issue. All right, now, so what is f prime of x? Okay, quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So this is 6x plus 3 minus 6x plus 2 so 5. So this is always positive. Okay, so we can't even apply the alternating series test here, but let's use the test for divergence. So we just take the limit as, well, I mean, technically to get the limit of this sequence, we would substitute n for x, but we could just go ahead and look at it like the limit as n approaches infinity of the a sub n. Okay, we can see that this is going to go to 3/2, so you have minus 1 to the infinity times 3/2. This is oscillating. This doesn't converge. So that means this is divergent. Right? Test for divergence. If this limit was equal to 0, then it wouldn't tell us anything. But that's why it's called the test for divergence. Because if this limit is equal to anything other than 0, or it's divergent, then you know the corresponding series is divergent. Okay, so the b sub n is 1 over e to the n, and that is always decreasing. So we can apply the alternating series test, which is you take the limit as n goes to infinity of the b sub n, and this is equal to 0, and so this is convergent. Okay, the b sub n here is, okay, now is this always decreasing? It seems like it would be, especially as n gets large, because the n cubed would take over, but we can check. So let's replace the n with a continuous variable. Okay, so f prime of x is equal to the derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So we've got 2x to the fourth plus 8x minus 3x to the fourth. Two x to the fourth minus 3x to the fourth is minus, so okay, 8x minus x to the fourth. Okay, when does this equal 0? So 8x minus x to the fourth is equal to 0. We factor out an x. Let's factor out a minus x. So we've got x cubed minus 8 is equal to 0. So difference of two cubes, you've got x minus 2, and then x squared plus 4x plus 16. Actually, this would be 2x. Okay, so I think this wouldn't result in real solutions. If we look at the discriminant, b squared minus 4 times, yeah, so the only real solutions here are x is equal to 0 and x is equal to 2. So if we take the limit, well, okay, actually, let's just plug in, instead of taking a limit, let's plug in x is equal to 3. So 8 times 3 is 24. 3 to the fourth is 81. So this is negative. Okay, so there you go. X is equal to 3. It's negative. It's never going to change signs after that because there's no other point where the derivative is equal to 0. So, and it's a continuous function. So, okay, this is decreasing. So we can apply the alternating series test. Okay, so what is the limit as n approaches infinity? We divide the numerator and denominator by n cubed. As n goes to infinity, this goes to 0, this goes to 0, so this goes to 0, so this is convergent. Okay, so the b sub n here is e to the 2 over n. Is this decreasing? Okay, well, as n gets bigger, this gets smaller. So, yeah, it's decreasing. Because like e to the x, the derivative of e to the x is e to the x. So if we're thinking about x is greater than 1, the derivative of e to the x is always positive. So this is increasing. This is monotonic increasing. So if this is, as n gets bigger, is always getting smaller, then e to that number is always getting smaller. It's not like, but also it's not like e to the x goes negative or anything. It's like, it's always positive. So it's just going to, it's monotonic increasing, or it's an increasing function, e to the x. And it'll always be getting smaller if the exponent is getting smaller. Okay, so we can use the alternating series test. So as n goes to infinity, this goes to 0. E to the 0 is 1, which is not equal to 0. So this is divergent. Okay, so here apparently the textbook is meaning like this is the same thing as sine, like all of this is in the argument of sine, which to me is really confusing. So the pi is within the argument of sine. All right, so in that case, we've let's simplify this trig function here. So we got n pi plus pi over 2. Okay, let's use this trig identity. Sine of A plus B is sine of A cosine B plus cosine A sine of B. So sine of A cosine B plus cosine of A sine of B. All right, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we've got cosine in pi. Okay, in pi. So when n is equal to 0, we've got 0, pi, 2 pi, 3 pi, 4 pi, etc. All right, if we think about the unit circle, cosine, it's 1 minus 1. 2 pi, it's 1. 3 pi, it's minus 1. 4 pi, it's 1. So this is alternating between 1 and minus 1, cosine of n pi. All right, but we're starting at 0, so we have minus 1 to the, if we're starting at 0, we want to start with 1. So we want to start with n. So yeah, when n is equal to 0, we want to start with it being positive 1 is what I'm saying. So n is equal to 0, we get this is equal to 1. So we want this to start by being equal to positive 1. So we want to just put n. Right? If this was n is equal to 1, we want to start this with as a negative 1, so we put n minus 1. Okay, so then when n is equal to 1, we start with n is equal to 0, we get cosine of 0 is 1. When n is equal to 1, we get cosine of pi is negative 1, and we get negative 1. You see? So we can write this as, well, let's bring this out front. Okay, this is really confusing how they put this pi like this, and to me that's really confusing. But okay, so all right, now we have an alternating series with where the b sub n is equal to this. Okay, is this decreasing? Yeah, 1 is constant, and then this is all the denominator is always increasing, so we can use the alternating series test. This we can see goes to 0, so this is convergent. Okay, sine of pi over n, starting at n is equal to 1, so let's analyze pi over n. When n is equal to 1, it's pi. When n is equal to 2, it's pi over 2, then pi over 3. Well, okay, what we can see is that, so we're starting at pi, right? Let's think about the unit circle. We're starting at pi, and then as n gets bigger, we're just getting smaller and smaller and smaller all the way back to 0, right? We never get to 0. We start at pi and we decrease, and then as n approaches infinity, we approach 0. Well, sine is always positive in this region, right? Sine is the y-axis. So from the start to finish, even at n is equal to 1, well, we start off at 0. Sine of pi is 0. But after 1, we're always, other than 0, we're always positive. And so with that, because this might not be an alternating series, depending on how this behaves, right? Just because you have this, we talk about this in the textbook section, just because you have this minus 1 to the n like this doesn't necessarily make it an alternating series. Alternating series, each term must alternate in sign. And if this was like alternating in sign for some circumstances, then you could have consecutive terms that don't alternate sign. But since this is always positive, then we do have an alternating series. And so the b sub n is this. Okay, now, is this decreasing? Well, we would say no, based on what we just looked at, right? We start off, we're getting, sine of pi over n is getting bigger in this region. But remember, it's all about the infinity portion. So wherever we're at, when we get to this point, that would be when, okay, well, yeah, actually, this would be pretty soon. This is pi over 2. So we start off at, yeah, so we wouldn't even be in that. We'd start off at sine of pi is 0. And then when n is equal to 2, we just go straight to here. So we're not even in this region. And then from there, we're always decreasing towards 0. So this does satisfy this is decreasing, this b sub n. So we take the limit. This qualifies for the alternating series test as n approaches infinity of this b sub n. As n goes to infinity, pi over n goes to 0. Sine of 0 is 0. So this converges. Okay, so here it looks like we have an alternating series with the b sub n. Yeah, this is always positive for all n. Okay, but is this decreasing? It doesn't seem like it is. So if we write out, okay, so when n is equal to 1, we've got 1 over 1, so just 1. When n is equal to 2, you've got 4 over 2. When n is equal to 3, you've got 27 over 6. .5. When n is equal to 4, you've got, so 64 times 4 is what? Yeah, there's no way this is decreasing. 256 over, and so then 4 times 3 is 12, 12 times 2 is 24, 10.7. So, yeah, I mean, I would assume that this is not decreasing, but let's see if we can, kind of prove that for all n. So, okay, we've got, so let's write out for like n is equal to 5. What do we have? Okay, so we've got 5 to the 4 over 4 factorial. And so that pattern will be for any n. You're going to have, this is equal to n to the n minus 1 over n minus 1 factorial. Okay, and so what we want to do is we want to show that b sub n, what we're assuming is going to be correct, is that this is going to be greater than the previous term for all n, right? The previous term is greater than the n minus 1th term is less than the nth term for all n. Okay. Now, since we've got this n minus 1 factorial here, let's use this definition, or this equality here, so that'll make it easier to evaluate this. Okay, so the denominators are the same, so we're just left with this inequality. Is this true for all n? Well, yeah, because you've got the same power. So you just compare the bases. This base is always bigger than this base. So yeah. Therefore, this, what does that tell us? That means this doesn't qualify for the alternating series test. This doesn't tell us that it's divergent, unfortunately. Okay, but it just tells us that it doesn't qualify for the alternating series test. But let's use the test for divergence. That should tell us the answer here. So we just take the limit as n approaches infinity of the a sub n. All right. So you can see with this alternating term here, if this converges to anything but 0 or diverges, then this whole limit diverges. So, all right. Well, yeah, we wrote out with that. So, what was it? It was, this is n to the n minus 1 over n minus 1. In fact, that doesn't tell us anything, but we wrote out that every term is going to be like, like 5 times 5 times 5 times 5 over 4 times 3 times 2. Every term is going to be like this. Well, you've got more terms up here than down here, and then furthermore being multiplied, and then furthermore, every one of these terms is bigger than all of these terms. So what does that tell us? Does that tell us that it's increasing or something? Well, I don't know what it tells us about the behavior of the function, but what it tells us is that one thing it tells us is that that n to the n over n factorial going from 1 to infinity is never going to be equal to 0, or like it'll never approach 0. Like we could look at it that way. In fact, it'll be, let's say this, it'll be always greater than 1, no matter what, which means it definitely can't be equal to 0 for any n. So in that case, this limit is definitely not equal to 0, and the test for divergence tells us that if this limit of the asymmetry is not equal to 0, then the corresponding series of that asymmetry is divergent.